selective filters. In this case, we applied the low pass Butterworth filter, a passband Butterworth filter. This is the frequency content of the breathing signals and the frequency content of the heart apex pulse signal. The principal frequency components are located in a different frequency range, but the frequency range is very close, so it's very important to apply a very selective filter. Here we show the preliminary results we obtained. Here we have the signals coming from, acquired by means of the transducer. This is the heart apex pulse, and it can be compared with the ECG signals acquired by simple, standard, conventional electrodes. And here we have the corresponds, each peak of these signals correspond to each QRS complex of the ECG signal. Here we have another example of the transducer signal output. Sorry. And the signal was filtered, and here we have the signal filtered in order to have the breathing signal, and this signal was compared with the output of the commercial device able to monitor, to detect the respiration signal, which in this case, which is the BioPack. As for high frequency analysis, we used the same transducer by a suitable switching device in order to detect the heart wall motion. From the medical literature, it is known that the heart wall motion, or the mechanical behavior of the heart, is very important, because when critical cardiac events occurs, the mechanical alteration of the movement of the heart occurs before the alteration, the modification of the electrical status of the heart. So, in this case, the early detection of this phenomenon could be very helpful in preventing cardiac disaster, crisis, or pathological events related to the heart, frequently lethal for the subject. The transducer can be, the scheme of the transducer is represented here. We have the piezoelectric element comprised between two layers of electrodes. These two electrodes are connected to a coaxial probe, and then we use the backing layer in order to maximize the sensitivity and the bandwidth of the transducer. Of course, we have to address these issues. These issues are very important. This is very crucial, the backing coupling between the transducer and the skin, the isolation, adaptability, and so on. The piezoelectric elements, as I said before, is the PVDF, having a low coupling coefficient, a good sensitivity, and the working frequency is about 2 megahertz. Here you have the results, and we used the transducer in order, we tested the transducer by using a target and by emitting an impulse. The pulse, the impulse was generated by the transducer. The transducer was suitably excited. The pulse travels travels towards the target. Then it was backscattered, and by evaluating the time delay, by evaluating the intensity, the magnitude of the backscattered echo, was possible to identify the position and then the movement of the target. And we arranged these experiments. Then, but these experiments are very, very preliminary. We tested these experiments on human subjects. It was volunteers to these experiments. And here we have the evaluation of the movement, of the motion of the heart wall, and it was compared by the ECG signals acquired simultaneously. Here we can, it's worthwhile noting that there's between two relative minimum or relative maximum of this curve corresponds to the complete cardiac cycle of the ECG signals. And these are satisfactory results, and it's promising for future development. The ultra-wideband radars is, the mechanism of the ultra-wideband radar is very similar to ultrasounds because the technique, the monitoring strategy is the same. It was based on pulse echo technique. We have a pulse generated, and by processing the backscattered echo, we can estimate the position and the nature of the target. Ultra-wide technology is a radio frequency technology, a mixture of conventional radio detection and ranging, and spread spectrum radio technology. Ultra-wideband means that we have the very, very short radio frequency pulses, about peak or nanoseconds, over a wide, very wide spectrum, ranging from 3.1 gigahertz to 10.6 gigahertz. We have about 7 gigahertz of spectrum, and the FCC, the Federal Communication Commission, usually allow this wide spectrum in exchange for a very, very low energy density. In comparison with, for example, other technology, radio frequency technology such as spread spectrum, for example, or narrow band, the ultra-wideband has a very low energy. And this is a very advantage because there's no interference with other devices working in the same frequency range. Then there are the very low electromagnetic energy emission. But the ultra-wideband technology, which is usually used for transmitting data, it's a communication wave, it can be profitably used in biomedical fields for biomedical application because we can measure, we have the contactless measuring approach. It's very similar to ultrasound strategy, monitoring strategy, but the very important, the advantage, the benefit of this technology is the non-contact. And therefore, the ultra-wideband signal